Alright, hello everyone. February the 1st. Alright, let's do this. Oh, this must be a new problem. Divide an array into arrays with maximum difference. You are given an array, nums, of size n and a positive integer k. Divide the array into one or more arrays of size 3, satisfying the following conditions. Each element of num should be in exactly one array. So okay. The difference between awesome any two elements in one array is less than or equal to k. Return 2D array containing all the arrays is possible. If it's not possible, to return set of the condition, return empty, and if there are multiple answers, return any of them. Okay, so we just need to find one. So given number is this, k is equal to 2, so we need to divide it up into 3. N is a multiple of 3, so yeah, we have to divide it up. Each number has to be in exactly one array. So you just divide the array into sets subarray of 3, right? And then we want the difference between any two elements in the array to be less than or equal to k. Isn't that we just sorted? Right? We just sort in and divide. Because they say the difference between any two elements must be less than or equal to k, which means it is better, right? Because adjacent ones, if we sort it, adjacent ones always have small difference, right? So if we sort it and then just take every 3, that should be the answer. Like, that is the best solution. But we can say, if we don't do that, right? If we don't do that, then we are always creating, like, if we swap anyone, right, then we are creating a bigger difference, right? At any position, if we swap, right, we sort it first. If any position we swap, then we are introducing a bigger value into one subarray and a smaller value to the other subarray, which will cause the difference to be bigger. Yeah, I think we'll greedy it, and since I'm done with the interview, so now we can go back to Java. Alright, let's Java this. I haven't done Java for a while. Okay, so what's the idea? The idea is actually let's we should do this or go, you know? That's what we should do. Alright, anyway, so what we're gonna do is we will sort the numbers. Okay, so I think it's arrays dot sort nums. Right, we'll sort the numbers. Then we will after we sort the numbers, we just go left to right. Every 3 we check, and every time we got a new one, then we reset the current difference. Okay, so we start from the second one. We compare, and then reset Compare, compare, reset. Compare, compare, reset. Yes, compare, compare, reset. So for right, if it's divisible, if I 3 is not equal to 0, right? It's not equal to 0. When equal to 0, we don't compare. Okay. Now we say if nums I, right? Nums I minus nums I minus 1. If this minus this is the difference is smaller or is larger than k, okay? Because I say less than or equal to, so if it's larger than k, when this is possible, then we shall just return, right, we'll return this. And keep going, and if int, oh, return this. Oh, what the hell? I shall return it empty. New int. I think it's this, right? Oh, I have the answer. Okay, so damn, new result equals new. Oh, yeah, that's the thing. You don't do this, and then you just forgot how Java works. Else right, else what? Else else is equal to, right? Then we need to put the previous 3 into so we need also a current. Right, we say int. Actually we can just do it here. Because we start with 0, so we say int int this current with a new int. That's just gonna be nums I, right? That's just gonna be num I. Actually, look at this. It's actually not too bad. I actually like it. What if we are here? The rule here is every time you press it, it will just go with both. And if we don't like it, we can always, you know what? I kind of like this one. Anyway, so we'll do this. Yeah, if it's equal to 0, we create a new current array. And I probably need to define it first. Current, okay? And then we'll say current is equal to this, right? And then every time if it's not, if it's this, we'll return this. Otherwise we're gonna say current dot push add. Oh, I cannot. It has to be a list. Oh, I can do size 3. Ah, true. I can do size 3. And then we just say current 0 is equal to nums I, right? And then here we say current I mod 3 is equal to nums I, right? Right, so if I equal to 0, I create a new one, and then I set a value. Next one, if it's good, I put I in it, and next one, if it's good, I put 9 in it. Next time I get it again, then I need to decide whether to push, right? I need to push. Then I can say, if current, right? If I have some current value, then I say if current is not equal to null, because this is a null at the beginning, right? Then we say res dot. Oh, that is not right. That is not right. Oof. Do we append? Do we add? Oh my. I know how many, right? I know how many. I do know. I can do this at the beginning. Come on, Like this is 3, right? And this shall be nums.length divided by 3. So I don't need this. I don't. All I need is another tracking. I can call j equal to 0, right? I just need tracking. And then this is just going to be res j, right? And then here res j, and then yeah, I'm filling up right here, right? And I can do res. It doesn't produce another one if it's this. Okay, that's actually pretty smart, right? Res j 0 is equal to this, and then res j1, res j2. When I equal to 3, we come in here. Then j need to plus equal to 1, right? J or plus plus. Yeah, j or plus plus. Then we will get the next one, which means we shall start with j equals -1. The first one becomes 0, and we set the value. Coming back, and then at the end we're going to return res. Oh my god, haven't done Java for a while, and then everything comes very, very slowly to me. Clunky, right? Just clunky. Oh, I think I have to Control C this. I don't think a yank works. Alright, is this right? Alright, looks to be okay. We did give it a shot. No. Oh, NA2, right? It's not just adjacent. It's NA2. Oh. That's right. So is this and, oh my goodness, and so that's true. And if the third one, so I mod 3 is equal to 2, and nums I minus nums I minus 2 is also larger than k. Actually, no, this is or, right? This is or. So, I don't know. Ah, no, it doesn't work. Oh, okay. Let's try with this. Yeah, alright, try it. Awesome. There we go. Very clunky. That's all I can say about this. Very, very clunky. It's a skill, right? Writing Java is a skill. I'm very clunky in writing Java again. Getting too spoiled by the simplicity of Python. Greedy solution. Sort nums and just try to put every 3 values into the answer. Need to check whether in fact, no, it is. We just need to check whether any 2 pairs within the 3 consecutive numbers satisfy the difference requirement. We count this as ON, yes. All right, that shall be it. Let's go back to, oh, I need to create a new folder. Because we go into February. No, because this one is completely new and it's Java. We do 2024 2.1.java. Okay. All right, let's take a look at the solution. Sorting, yes. Maybe all we need to do is check these 2. Yeah, I think all we need is check these. I don't even need to check the consecutive ones. Nah, because if the consecutive ones fails, then you can fail early. So you don't have to go one more round. So there is a reason for doing consecutive check as well. So, I guess it's okay. I mean, we probably can. Nah, it's all right. It's all right. This only do this check. Oh, look at that. It's ON login. Dear me. I forgot the sorting part. Yeah, that is a better solution, a better implementation. This is too clunky, right? Yeah, we do 1 check and return new int 0, 0. Oh, that is interesting. Oh. Okay, that's actually better. I want to do it again. That's actually a better way of doing it. So this is all the same. I don't need this, and all I need to do is plus equal to, right? That's all we want. We say this is plus equal to 3, right? And then all we need to check, yes, if nums I, right, minus nums I minus 1 minus 2, right? Oh, we start from 0, so it's I plus 2, right? It's I plus 2, and this is I. If this is smaller or equal, no, if this is larger than k, right, then I'll return new int this, right? Otherwise, we say res I divided by 3, right? I divided by 3 shall equal to new int this new int this nums I plus 1 and nums I plus 2. Oh, that's way better. That's way better. Better implementation. Always looking for better implementation. Yep. Way better. Probably faster too. It's about the same. Alright, that is fine. So we go back here, we go, C2Z, we go down here, and then we do this. So yeah, if you take a look at here, because I'm waiting for the second key, right? And this I still put in here, that's something actually that's causing all the trouble, right? So all I need to do is do this, and then immediately go to the right parentheses, right? And if I type this, it should be keep on the right hand side. Because if it's here, it's fine. I just do this, and then we call back, and then yeah. Yep, I think I'm gonna change how I do it. Okay, so we're done with this. Let me turn this off and move on to this problem. We have the idea, so I think we can do it. Go right for it. But before that, yeah, let me feed my cat. Alright. Alright. Okay. Okay. Alright. What else? Oh my god. He kept licking the same piece of meat, but just didn't eat it. What? Come. I gotta set up NeoVim for Java. Not even sure if that's a good idea. Alright, I'm back. Should I set up NeoVim for Java? Or just forget about it and then we just go Rust? Maybe we should just go for Rust. Alright, so we already handled this problem yesterday with all the notes. So basically we're gonna go from top to bottom. We will record each path, have a start and end, right? We'll have a start and end as the key, and then we'll have the bit mask. Huh?
It's chocolate bar.
I didn't even use it yesterday.
Well, maybe from days ago, I don't know.
Well, sorry. We'll have each path, right, represented by some stuff. Actually, we need to have, so this is the keys, right, for each path. It can be anything, but I'm just gonna use this. Wait, well, what is this? So it's each individual path, right? Each individual smallest unit of the path. So we go from some place down, right? And then how do we keep track of this? Yes, that's the next question, right? We have this. We can turn this into an adjacency list. And what's this S represents again? S represents edge between I and to its parent. Okay, so that's fine. We can get all the edges. We can get all the edges, and then as we go, we get a path. So from the current root towards all of its, right? All of its. Oh, from the current root to all of its descendants. That is going to be a lot. My n is 10 to the 5th. That is going to be a lot of paths you need to keep track. It's a good question. How many paths are they going to be? Well, we have n already, right? 1, 2, 3, 4, 5. And then we have this 6, 7. We have 8 in this case. And let's say if we have a giant one, right? If we have a giant one, just like this, right? Everybody is the same to the root. Now we have a giant one, and you have 10 different. Yeah, as a 1 plus 2 plus 3 plus 4. So I have on the scale of n squared. Actually, this method is not going to work. You have on the scale of n squared the total number of paths, and I don't think it is possible to go through every one of them. Ooh, we need something smarter. We absolutely need something smarter than how? How? we can traverse it, but we can only traverse it once, right? And as we traverse it, we can say, okay, give me all the paths with me as a root. That is fine, right? With me as a root, give me all the paths towards the, or you can say as I go through, I'll keep all the paths, the path ending at me, okay? The path ending at me, that's only going to be one path that ends at me, right? One path that ends at me. But then you have many roots, right? You have many roots. You can have just start from the root, from 0, okay? Just start from 0. And then you add some position and have a path. It all starts from 0, right? It all starts from 0. But then how do you handle a path, let's say 3, 1, 4, like a path like that? So you have to consider everything as its own root. If you consider everything as a root, like I'm at 4, then I have 2 roots, right? If I'm at bottom, I have all of these. Each one can be a root. Then it's O(n) squared. We cannot do O(n) squared. Can't do it. Yeah, I think the method I had yesterday will not work, unfortunately. Then what? Maybe we can work on S and try to see if there is a path in between. Like the S is all the nodes. Is it the nodes has any tree rooted at 0? Consider the n nodes numbered. Tree is represented by a 0 index array. Now this no kind of, because it can be anything. Like a 2 can be here, right? A 1 can be here. I can just change this and then I can change the tree. The number, the number doesn't really matter that much. It's just going to be a tree with, yeah, I can represent it in a different way, right? A real adjacency list with all the edges, right? With all the edges. And then we can start from the, we can basically start from any, we can start from any node, and start go, right? Yeah, this method doesn't work because it can be O(n) squared. The number of total paths can be O(n) squared, and that is not going to work. So that's what I'm thinking. Is it possible if we go from S? So we know that every single one is, right? Then we try to find, how are you gonna find? How are you gonna find the total number of palindrome substring, not even substring, the subsequence, right? Palindrome subsequence within S, that is also going to be a lot of work. And then you have to check if a subsequence can form. How do you check? I mean, they're all connected, right? They're all connected. But yeah, like I said, what if you do like ABA, right? You do ABA, and how do you know that they're... You can't, can you? Edges. Now we can say like this edge is connected only to this edge and this edge, right? 1, 4, this edge is connected to 1, 3, and 1, 0, and that's it. All right, that's it. So if I want to connect this to this, so connect to this one will connect to this, and this need to connect to this, and that's how we form a path. Edges connection. Edges connection. I don't know. Edges connection. Right, so I can say edges connection 1, 3 is only connected to 1, 4. Right, 1, 4 is connected to 1, 3 and 1, 0. I'll call it 0, 1. Smaller always at the front. Right, and then 1, 0, 0, 1 is connected to 1, 3 and 0, 2. Right, 0, 2 connected to 0, 1 and 2, 5. And 2, 5 connected to 0, 2. Right, I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's the same as this. 1, 2, 3, 4, 5. The first one, ignore. So 1, 2, 3, 4, 5, right? So these are the edges. I can even, because we have A, this one is, we don't have to consider C, A, B, C, right? So I can do, let's say, an adjacency list of, 1, right? And this, we can go here. It has a parent as 0, right? Which means 1 has a parent as 0. So this, and all I need to find is these two, right? Because that position is 1. So who's connected to me, right? Who's connected to me? So in this case, 0, 1, 2, 3, 4, right? So 3 and 4 is connected to me. And then 2, okay? 2 is this, who is connected to me, so who has me as the root, as directly connected to, so this is this one. 5, right? 5 is connected to me. 3, so I'm 3. 3 connected to 1, right? So all the connection that 1 has, 3. So 3 is this edge, right? 3 is this edge. So all the edge that, I'm gonna do it again. I think I'm missing one, right? 1 is this edge. This edge is connected to, so 1, 0. Yeah, you're missing one. You're missing one here. 1, 0 has one more. is 1, 3. So it's two things. One is what you are connected to and what your parent is connected to. So for 1, these two are connected, and also the parent is 0, so whatever 0 is connected to. So 0 is also connected to 0, 1, 2. So 2 is also part of it. Right? So this edge is connected to this, this, and this. And 2, this edge is connected to 1 and 5. Right? 1 and 5. Three, 0, 1, 2, 3. 3, so all the other one that is 1, so which is 4. Right? And also it connects to 0, so all the other one that is 0, which is 1. So 3 will connect to 4 and 3 connect to 1. That's correct. Right? This connects to this and this connects also. Yeah. Also 1, 0. That's true. We also have 1, 0. Right? 1, 3 connects to 1, 4 connects to 1, 0. So 3 connects to this, and also because its parent is 1, so whoever is connected to 1 is its 4, and wait, whoever its parent is connected to. No, whoever its parent for sure. Yes, it's its parent. Okay, its parent. So my current edge is from me connected to my parent, right? So who is connected to this is who my parent connected to and who connects to me. So that's the two things. So for 1, 0 is I need to put a 0 in it, but we don't put 0 because my parent is 0. It doesn't lead to anywhere, and is just who is connected to me, and I have 2. Right, is connected to me. But also I have my parent. Right, so who else is connected to my parent? Who else is connected to my parent? Right? So I need to go with 3 scenarios, right? Who connected to me? My parent, right? My parent. Oh, do you need to do my parent? This one. Yeah, oh wait, hold on. I don't see I need to do my parent. My current one, who's connected to me, and who's connected to my parent, right? Who's connected to my parent, which is to say who my parents' parents are. Right, my parents' parent. Yes, my parents' parent. So my parents' parent, and so yeah, my parents' edge, right? My parents' edge, and who connected to my parent. So that's whose parent is my parent, right? Whose parent is my parent. So my parent is 0. So whose parent is also 0. 2, its parent is also 0. And who's connected to me? I'm 1. So yeah, the 3 things. So it's who's connected to me, right? Who's connected to my parent, right? And who my parent, who's my parent's parent. That's the three layers for each one. So that's why 1 has these 3 edges, and 2 has who's connected to me. That's 5. Who's connected to my parent. That's a 1. And who's my parent's parent? We don't have a parent's parent. For 3, who is connected to me? Nobody is connected to me. Who's connected to my parent? My parent is 1, so who's is 1? 4. And who's my parent's parent? It's not really my parent's parent. Who's my parent's parent? That's 1, right? That's just 1. It's not really my parent's parent. My parents. What is my parent's edge? Right, and my parent. And who's my parent? Exactly, that's it. Who's my parent? Excluding 0, right? So we do 4. Again, who's connected to me? Nobody connected to me. Who's connected to my parent? My parent is a 1. And who's connected to my parent is 3, right? And who's my parents? Who is my parent is 1, right? So we can do that. And next one is 5. Nobody connected to me. Who's connected to my parent is 2. So only me is that, so that's no good. And so 5 is only connected to. So these are the connections among the edges, right? Among the edges. So can we build a graph based on this? 1, 2, 3, 4. 2 and 1, 2 will be going to 5. And 3 is going to 4. And 3 is going to 1. Yeah, so 1, 3, 4. They're also can go 1, 3. 3, 4. Yeah, they all connected. That is, yeah, because 3 is connected to 4. And 1 is connected to 3, 1 connected to 4, 1 connected to 2. Right? 1 can go to 2. Ooh. No, 1 can go to 5. That's true. And 1 can go to 3, 1 can go to 4. And 3 go to 4 via 1. That's not really yeah, these 2 edges are connected. These 2 edges are connected. So we're just doing what edges are connected. I have a 3 connected to 4, 4 connected to 1. You can't do 3, 4, 1, right? No, you cannot. Okay, this is not gonna work. I have to figure something else. What if we say we only find all the paths rooted at 0 and see if from there we can find some stuff. So if we find all the paths rooted at 0, then we have 0, 1. Yeah, we can just say we have 1, which is C. We have 3, which is CA. We have 4, which is CB. 2, which is A, and 5, which is AC, right? Any of this is, then good, okay? If yeah, we can try this, right? We can try this, and from here we can pick out a few palindrome already. This we can do. Okay, that's ON. And then how do we identify the ones not going through 0, right? I mean, for here, everyone is crossing the 0, right? 1, 5. Everyone is crossing the 0, so that's why this one will work. But what if I have, let's say this one is A, you know, instead of a B, this is A. Then we'll have something crossing 1. You know what? I think that is a better example. I want to try. So we have something that does not cross. So again, we can do C, A, 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 and then C. Right? We do this. Simple enough. So again, that's right. 0, 4 is CA. Okay, it's CA, and everybody else is the same. So in this case, we can compute again. Crossing 0 is easy, right? So we have a C, so it can be fit like this one fits CA. We have another CA, right? Basically, oh, that actually doesn't work because it's on the same side. All right, C is go down to 1. We need on the other side. Because on this side, that's the parent edge. So everybody else, yeah, is on the same side. So it has to be on the other side. So we'll have the CA, we'll have the CAC, right? And on this side, we can do CA with the other CA. I'll have another CA with the CA. Yeah, those all work. But also the AA, right? We cross from 1. Cross from 1. Oh. Cross from 1. Yeah, it's these crossing things are, when you cross, you have to cross a root, right? You cross a root and you go to the other side. And let's say if this is the root we're looking at, anything that's crossing this root, go to the other side, it will be the same as crossing this root. So we'll have already considered. Which means for each crossing that we need to consider, we only need to consider starting from the current one as a root. So if we, recursion, so we say I find all the paths rooting at this, which is finding all the paths rooting at 1 and finding all the paths rooting at 2, right? And if we have all the paths rooting at 1 going all the way down, right? And we add a C, so we can check, right, how many paths there are. But there will be a lot. That's the thing. There will be a lot. Oh, it's not just going. Okay. And depending on the leaves, right? When we say path, we say go all the way down. So we're gonna have, however many paths, and each path is gonna be a giant string, right? Each path is going to be a giant string, and within this giant string, it goes step by step, right? Now we say we're gonna add a value C to it, which we're trying to say right? If we are considering if there's any palindrome on this side, right? On this side of the tree, which is meaning if we cut it, right? If we break at some point, then this will become a palindrome, right? That's what we're trying to say. But then how? How do we know? Well, we add a C, right? Which means if I have an array to represent its bit mask starting from here. So we have a bit mask for this, and we have a bit mask for these two, we have a bit mask for these three, and then going all the way down. Does that even make sense? That's just one, right? That's just one. That's just one path. So for each one path, you're gonna have a counter of bit masks. Okay, a count of bit masks, like incremental bit mask. I have another path, so we're gonna have an array of counters, right? We'll have an array of counters. Each counter represents the count of bit mask of each incremental path substrings, right? All the way down to the leaf. And then when you add this, we need to go through all the paths, right? All the paths to see how many matches I have, right? And once you have that, you need to add yourself into each bit mask. See, that's you O(n) squared again, right? Because you have so many paths. You have so many paths. Lord. Oh. All right, I'm gonna stop right here. Yeah, idea doesn't work, but there are 2 hints. I'm tempted. Yeah, whatever I think right now, it's always O(n) squared. I don't like it. I don't like it at all. Anyway, I'll stop right here. I'll see you guys tomorrow. Adios.